The B-17 once returned safely to base with a 20-foot section of its wing completely torn away, a testament to the incredible engineering that earned this aircraft its legendary status. The Flying Fortress stands as one of World War II's most remarkable engineering achievements. This Boeing B-17 Flying Fortress combined revolutionary design features, advanced defensive systems, and structural innovations that transformed aerial warfare. The Flying Fortress bomber carried up to 4,000 pounds of bombs, defended itself with up to 13 machine guns, and could sustain devastating battle damage while protecting its crew. This article explores the groundbreaking engineering solutions that made the B-17 Flying Fortress World War II's most iconic heavy bomber, from its revolutionary four-engine configuration to its advanced flight control systems and combat-tested structural design. Revolutionary design features. Boeing's engineering team broke conventional aircraft design principles when they developed the B-17 Flying Fortress in response to the 1934 Army Air Corps specification. Their innovative approach would set new standards for bomber aircraft design and capabilities. The most striking feature of the Flying Fortress was its revolutionary four-engine configuration, implemented at a time when twin-engine designs were standard. This bold engineering choice enabled the bomber to carry 2,000 pounds of payload across distances between 1,000 and 2,000 miles at speeds of 200 to 250 mph. The aircraft utilized Wright R1820 Cyclone engines, which evolved from 920 to 1,200 horsepower as the design matured. The B-17's aerodynamic design enabled exceptional high-altitude performance, with a service ceiling ranging from 25,000 feet, depending on the bomb load. A crucial innovation was the integration of GE-built turbo superchargers, which compressed outside air before feeding it back to the engines, enabling efficient high-altitude operations. This engineering solution gave the Flying Fortress superior performance above German anti-aircraft artillery ranges. The B-17E represented a remarkable advancement in structural engineering, incorporating several critical changes that enhanced its performance and durability. Among the most notable improvements was the fuselage extension, which was lengthened by 10 feet, providing additional space and improving overall aerodynamics. Complementing this modification were significant enhancements to the aircraft's tail assembly. The vertical tail fin and horizontal stabilizer were substantially enlarged, contributing to greater stability and control during flight. Furthermore, the structural components of the B-17E were reinforced, ensuring greater resilience and reliability under operational stress. While increasing the aircraft's total weight by 20%, these reinforcements also made it more robust and capable of enduring the rigors of combat and heavy-duty missions. The aircraft's all-metal construction proved crucial for combat survivability. Boeing engineers developed the airframe with redundant structural elements and damage-tolerant design principles. The final B-17G variant incorporated all previous structural improvements, resulting in the definitive Flying Fortress design that would serve throughout World War II. The engineering team's focus on structural integrity paid dividends in combat, where the B-17 earned a reputation for surviving severe battle damage. This durability, combined with its advanced defensive armament system of 13.50 caliber machine guns in the G model, made it a formidable aerial platform. The aircraft's dependability led Army Air Force leaders to adapt it for various missions beyond its primary bombing role, including photographic reconnaissance and air-sea rescue operations. Engineering the defensive systems. The defensive capabilities of the Flying Fortress evolved dramatically through its service life, establishing new standards in aerial combat protection. The aircraft's defensive systems underwent continuous refinement, progressing from an initial configuration of 4.50 caliber machine guns to an impressive array of 13 guns in later models. The B-17's defensive architecture centered around sophisticated powered gun turrets. The Sperry Ball turret, a revolutionary addition, provided crucial ventral defense through an electro-hydraulic system that could rotate 360 degrees. The turret's twin .50 caliber M2 Browning machine guns delivered an impressive combined rate of fire of 1,600 rounds per minute. Key defensive positions included a twin-gun-powered top turret and ventral ball turret, tail gunner position, waist gun stations, and nose turret added in later models. The challenges faced during combat operations prompted substantial advancements in the protection of bomber crews, leading to innovative and practical solutions. A comprehensive study conducted in 1942 revealed that the majority of injuries sustained by bomber crews, approximately 70%, resulted from low-velocity projectiles and fragments of shattered aircraft components. These findings underscored the need for enhanced protective measures to safeguard personnel in hostile environments. In response, engineers devised an array of cutting-edge armor systems that addressed the vulnerabilities identified in the study. One of the most significant innovations was the use of manganese steel plates. These plates, crafted as thin, overlapping squares measuring just 1 millimeter thick, provided a unique combination of flexibility and durability. This design allowed for effective protection without compromising the crew's mobility or the aircraft's functionality. Additionally, the strategic placement of armor was a key focus of these improvements. Engineers concentrated the protective materials around critical crew positions, such as the cockpit and gunner stations, where personnel were most exposed to enemy fire. This targeted approach maximized the efficiency of the armor while minimizing unnecessary weight. To further enhance crew safety, a quick-release system was incorporated into the design of the body armor. Weighing approximately 13 pounds, the protective gear featured an emergency removal mechanism, enabling crew members to shed the armor swiftly if needed, such as during an evacuation or other critical scenarios. These combined measures significantly improved the survivability of bomber crews, reflecting a dedicated effort to adapt to the harsh realities of aerial warfare. The B-17F marked a crucial advancement in combat visibility with its enlarged, nearly frameless plexiglass bombardier's nose enclosure. This design enhancement significantly improved forward observation capabilities while maintaining structural integrity. The later B-17G variant introduced the Bendix-built chin turret, addressing a critical vulnerability to frontal attacks. The defensive system's effectiveness relied heavily on the combat box formation, where interlocking fields of fire from multiple bombers created a formidable defensive network. When fully implemented, this formation could bring approximately 700 defensive machine guns to bear on enemy fighters. The system proved so effective that it influenced bomber design philosophy throughout World War II and beyond. The integration of these defensive systems required careful engineering considerations. The top turret and ball turret utilized advanced electro-hydraulic systems capable of traversing at 50 degrees per second. This rapid response capability, combined with electrically fed ammunition systems, provided gunners with the tools needed to engage fast-moving fighter aircraft effectively. Manufacturing innovations. The wartime demand for the Flying Fortress sparked an unprecedented manufacturing effort that redefined aircraft production. Boeing and its partner companies developed innovative mass production techniques that would shape the future of aerospace manufacturing. The transition from craft-based manufacturing to assembly line production marked a fundamental shift in aircraft building. Boeing's production capacity grew dramatically, increasing from 60 B-17s monthly in 1942 to an impressive 362 aircraft per month by March 1944. This remarkable achievement resulted from a unique wartime collaboration between multiple manufacturers, with Boeing serving as the primary manufacturer, and also involving Douglas Aircraft, Lockheed's Vega subsidiary, and numerous component suppliers. The workforce underwent significant changes, with thousands of women joining production lines and helping achieve a total production of 12,731 Flying Fortresses. This industrial mobilization required expanding existing facilities and establishing new production sites across the country. The implementation of systematic quality control measures proved crucial for maintaining consistency across multiple production facilities. A key innovation was the development of comprehensive pre-flight checklists, which enabled YB-17s to accumulate 1.8 million flight hours without incident. The manufacturing process required precise coordination among suppliers, with the B-17's complex structure demanding meticulous attention to detail. For example, a single nose section contained more than 50,000 rivets, 8,000 different parts, and components from over 1,500 suppliers. The shift from traditional manufacturing methods to mass production necessitated significant advances in material standardization. Engineers developed new processes for working with aluminum alloys and other advanced materials, ensuring consistency across all production facilities. The manufacturing system required a revolutionary change in production technology, moving away from individual job shops to standardized assembly lines. This transformation demanded greater part standardization and refined job processes due to the aircraft's complexity. The success of this approach influenced post-war aircraft manufacturing methods and established new industry standards for quality control and production efficiency. Flight control systems. The engineering of flight control systems in the B-17 Flying Fortress represented a unique approach that prioritized reliability and combat survivability. Unlike its contemporaries, the B-17 utilized a minimalist hydraulic system design that would prove crucial in combat operations. The B-17's hydraulic system demonstrated remarkable engineering restraint, operating only the cowling flaps and wheel brakes. This intentionally limited hydraulic implementation meant fewer vulnerable fluid lines throughout the aircraft, significantly reducing the risk of system-wide failures from combat damage. The simplified design proved especially valuable during combat operations, where maintaining control despite battle damage was crucial. The Flying Fortress was equipped with an advanced and robust mechanical control system that operated the aircraft's control surfaces through an intricate network of cables running throughout the fuselage. This engineering design was not only innovative for its time, but also provided significant operational advantages, particularly in the demanding conditions of combat aviation. A key feature of this system was its redundancy. Each control surface, such as the ailerons, elevators, and rudder, was connected to multiple cables, ensuring that if one set were damaged during combat, others could still maintain functionality. This redundancy dramatically improved the aircraft's survivability and the crew's ability to maintain control in hostile environments. In addition to redundancy, the mechanical system amplified pilot inputs, enabling more precise and effective maneuvering despite the substantial size and weight of the aircraft. This mechanical advantage reduced the physical strain on the pilot and contributed to the aircraft's responsiveness, making it easier to handle during complex flight operations. The design also minimized vulnerability to combat damage. Unlike hydraulic or electronic systems, which could be rendered inoperative by a single critical hit, the mechanically operated controls were less susceptible to catastrophic failure. This resilience was especially important during missions over heavily defended enemy territories, where aircraft were frequently subjected to intense anti-aircraft fire and attacks by enemy fighters. Moreover, the system proved highly reliable under extreme conditions. It was unaffected by the severe cold temperatures at high altitudes, which could cause hydraulic fluids to freeze or electronic systems to malfunction. The system's effectiveness was particularly evident when compared to contemporary bombers that relied heavily on hydraulic controls. The B-17's mechanical system allowed pilots to maintain aircraft control, even after sustaining significant combat damage. The B-17 pioneered several groundbreaking pilot interface systems. The Pilot Director Indicator, manufactured by Roller Smith Company, featured 4 graduation marks on either side of center zero, enabling precise course corrections. This system integrated with the C-1 autopilot, which utilized 2 spinning gyroscopes, the flight gyro for roll and pitch detection, and the directional gyro for yaw control. A significant innovation emerged from early B-17 operations when Boeing introduced the first aircraft checklist system. This development came after a critical accident in 1935, leading to the implementation of systematic pre-flight procedures that enabled crews to fly 1.8 million hours without incident. The integration of the Norden bombsight with the aircraft's control systems marked another engineering milestone. During bombing runs, the system could assume control of the aircraft through the C-1 autopilot, guiding it precisely to the target release point. The bombardier could take complete control of the aircraft through this interface, while the PD provided crucial flight path information to the pilot. These control systems worked in concert with the Honeywell Key-1 autopilot, which used electrical signals to control servo-connected control surfaces, allowing either the pilot or bombardier to command the aircraft effectively. This dual control capability proved essential during precision bombing missions where exact aircraft positioning was crucial for accuracy. Power plant engineering. The power plant engineering of the B-17 represented a masterpiece of wartime innovation, combining robust design with operational flexibility. The aircraft's Wright R-1820 Cyclone engines delivered 1,200 horsepower each, enabling exceptional performance at altitudes up to 25,000 feet. The B-17 bomber's engine mounting system was a marvel of practical and efficient engineering, specifically designed to support both the operational demands of wartime and the need for streamlined maintenance. Central to this system was a circular tubular frame with a diameter of approximately 2.5 feet. This sturdy frame provided a secure foundation for each engine and was anchored to the aircraft's firewall by 4 angled support legs. These legs not only enhanced the structural integrity of the mounting system, but also helped distribute the weight and vibrations of the engine more effectively, ensuring stable performance during flight. One of the most remarkable features of this design was its emphasis on rapid engine servicing and replacement. With an experienced maintenance crew, a complete engine could be removed and replaced within just 5 hours, a critical advantage in the high-pressure environment of wartime operations where minimizing downtime was essential. This efficiency was further facilitated by the inclusion of quick-access panels, which allowed technicians to perform routine maintenance tasks swiftly and without the need for extensive disassembly. Additionally, the engine mounting system was designed with integrated accessory mounting points, enabling the seamless attachment of auxiliary systems such as fuel pumps, generators, and other necessary components. This integration reduced the complexity of installation and maintenance, contributing to the overall reliability and functionality of the aircraft. The combination of robust structural design, ease of access, and integrated systems made the B-17's engine mounting system not only a technical achievement, but also a practical solution tailored to the operational realities of World War II. This innovation ensured that the Flying Fortress remained mission-ready, even under the intense demands of sustained combat operations. The B-17 bomber's cooling architecture was a sophisticated and meticulously designed system that played a critical role in ensuring the reliable operation of its engines under the demanding conditions of sustained flight and combat. At the heart of this design were advanced intercooler systems, which were strategically positioned within the engine nacelles to maximize efficiency and airflow management. For the outboard engines, engineers placed the intercoolers vertically behind the firewall, a location that provided optimal airflow while maintaining structural integrity. In contrast, the intercoolers for the inboard engines were located aft of the nacelle and the front spar. This arrangement accommodated the unique spatial and thermal demands of the inboard engine configuration, ensuring consistent cooling performance across all 4 engines. To complement the physical layout of the intercoolers, the B-17 featured a comprehensive temperature control system that allowed for precise management of engine cooling. The control interface for this system was conveniently located on the right cockpit wall, within easy reach of the co-pilot. This control panel allowed the crew to monitor and adjust cooling parameters as needed during flight. A key component of this system was the adjustable intercooler exit air valves, which regulated the flow of air through the intercoolers. By fine-tuning these valves, the crew could optimize cooling efficiency based on specific operational conditions such as altitude and engine workload. Additionally, hydraulically actuated cowl flaps were integrated into the system to provide enhanced control over engine temperature. These flaps could be opened or closed to modulate airflow around the engine, further improving the cooling process and preventing overheating. The system maintained optimal engine temperatures through a network of ducting that channeled air from wing leading edge openings through the intercoolers, exhausting through distinctive mid-wing slots behind each engine. The B-17's fuel system demonstrated remarkable engineering sophistication with its multiple redundancies and transfer capabilities. Each wing contained 3 tanks, with provisions for additional outer wing feeder tanks. The aircraft's fuel system was designed with a specialized configuration that optimized operational efficiency and extended range capabilities. At its core, the system featured distinct tanks tailored to meet the specific needs of individual engines. A 425-gallon tank was dedicated exclusively to engine number 1, ensuring a robust and consistent fuel supply for its operation. Similarly, a 213-gallon tank was allocated for engine number 2, providing it with a steady source of fuel. In addition to these primary tanks, the system incorporated multiple feeder tanks that enhanced the aircraft's range and flexibility during missions. These auxiliary tanks allowed for the redistribution of fuel as needed, ensuring that all engines received adequate supplies even during prolonged flights or when fuel consumption patterns varied. This carefully engineered configuration demonstrated a thoughtful approach to maximizing efficiency and performance, reflecting the meticulous attention to detail that characterized the aircraft's overall design. Engineers incorporated an innovative fuel transfer system utilizing 2 selector valves and an electrical transfer pump, allowing fuel routing between any tank and engine. The system maintained reliable fuel pressure through booster pumps, generating 12 to 16 psi, crucial for high-altitude operations. The total fuel capacity reached an impressive 3,600 gallons, with all tanks filled, while the combat configuration carried 2,780 gallons. This sophisticated fuel management system enabled the Flying Fortress to conduct long-range bombing missions while maintaining operational flexibility. The power plant engineering incorporated advanced turbosupercharger controls, with the B-17E featuring Eclipse Type 7 regulators that automatically adjust Westergate positions based on exhaust pressure and cockpit settings. This system evolved further in the B-17G, which introduced electric motor-controlled Westergates, requiring a DAC inverter for operation. Structural durability. Structural integrity formed the cornerstone of the Flying Fortress's legendary status, with its robust design enabling aircraft to withstand unprecedented levels of combat damage. The B-17's structural engineering represented a significant advancement in military aircraft design, incorporating multiple redundant systems and innovative damage-resistant features. The B-17's structural framework utilized an advanced thickness to projectile ratio exceeding 0.1, which significantly damaged the macro damage size from projectile impacts. The engineers adopted a comprehensive strength-based design strategy to enhance the aircraft's durability and resilience. This approach utilized multiple load-bearing parts, ensuring that the structural integrity of the aircraft remained intact, even under significant stress or damage. Key stress points were reinforced to withstand the demands of high-intensity operations, while redundant structural members were integrated to provide additional layers of support and reliability. In critical areas, laminated wood components were employed, offering a combination of flexibility and strength that complemented the overall structural framework. Additionally, advanced aluminum alloys were incorporated extensively throughout the design, leveraging their lightweight yet robust properties to improve performance and efficiency. This meticulous blend of materials and design elements resulted in an aircraft capable of withstanding the rigors of combat and operational challenges. The Flying Fortress earned its reputation through remarkable combat survivability. The aircraft's damage tolerance capabilities stemmed from innovative design features that allowed it to maintain structural integrity despite severe battle damage. The B-17's remarkable combat resilience was evident in its carefully engineered features designed to withstand and mitigate damage. Among these were advanced impact response characteristics that played a crucial role in maintaining the aircraft's integrity during hostile engagements. The metal sheets used in the aircraft's construction were specifically designed for spallation resistance, reducing the risk of material fragments detaching and causing secondary damage. Additionally, engineers incorporated methods to control crack propagation, ensuring that any structural fractures resulting from impacts remained localized and did not compromise larger sections of the airframe. Petal formation, a phenomenon that occurs when metal deforms under high-velocity impacts, was also managed through precise material selection and design. This minimized the disruption to the aircraft's surface and maintained aerodynamic performance. Furthermore, the structure demonstrated enhanced tolerance to holes and dents, allowing it to endure significant wear and tear without compromising flight capability. The aircraft's structural design enabled it to withstand various types of combat damage while maintaining flight capability. Engineers developed specific parameters for assessing impact failure characteristics under load conditions, with residual strength calculations determining post-damage flight worthiness. The B-17's maintenance system brought a groundbreaking approach to aircraft repair, streamlining the processes of damage assessment and restoration through well-defined and systematic protocols. Central to this system was a meticulous damage classification framework, which allowed maintenance teams to differentiate between critical structural compromises and non-critical damage. This classification enabled the efficient prioritization of repairs, ensuring that essential structural issues were addressed promptly, while less urgent matters were scheduled accordingly. The repair procedures were standardized to enhance consistency and efficiency across maintenance operations. These procedures included protocols for replacing damaged sheet metal, reinforcing compromised structural members, and ensuring that components were designed for accessibility, which simplified both routine maintenance and emergency repairs. This uniformity not only reduced downtime but also ensured the durability and reliability of repairs, even in the demanding environments of wartime operations. To facilitate clear communication and accurate tracking of repair statuses, the system utilized Form 1 documentation. This documentation was paired with a color-coded indicator system that conveyed the operational readiness of the aircraft at a glance. A red X marked an aircraft as grounded, signaling that it was unfit for flight until critical repairs were completed. A red diagonal indicated that delayed maintenance was required but did not immediately compromise flight readiness. Finally, a red dash was used to denote the need for inspection or to highlight specific notations, ensuring that even minor issues were systematically monitored. Engineers developed specific repair manuals detailing procedures for various damage types, ensuring consistent maintenance quality across different service facilities. The aircraft's design incorporated accessibility features that facilitated rapid repairs, crucial for maintaining operational readiness during combat deployments. The structural durability of the Flying Fortress benefited from extensive testing programs that validated its design principles. Wind tunnel testing and combat performance evaluations provided crucial data for the continuous improvement of structural components. This systematic approach to structural integrity made the B-17 one of the most reliable aircraft in military service, with documented cases of severely damaged bombers successfully returning from combat missions. Crew support systems. Life support engineering aboard the Flying Fortress represented a complex integration of systems designed to keep crews alive and functioning in the hostile environment of high-altitude warfare. The B-17's crew support systems underwent continuous refinement throughout its service life, addressing the challenges of sustained operations above 25,000 feet. The B-17's oxygen delivery system featured remarkable redundancy with 18 Type G1 oxygen tanks distributed throughout the airframe. Engineers developed a sophisticated distribution network comprising 13 to 12 oxygen regulators for individual crew stations, Type 1 flow indicators for system monitoring, diluter demand regulators providing altitude-appropriate oxygen mixtures, and specialized brass fittings connecting 5 16-inch aluminum distribution lines. The system's criticality became apparent at high altitudes, where crew survival depended entirely on reliable oxygen flow. At 25,000 feet, crew members would lose consciousness within 3 to 5 minutes without supplemental oxygen. Engineers addressed this risk through an innovative walk-around bottle system, providing 13 Type 4 portable oxygen units that enabled crew mobility during long missions. Temperature management posed a substantial engineering challenge for the B-17, especially given the extreme cold conditions encountered at operational altitudes, where temperatures could plummet to as low as 50 degrees below 0 Fahrenheit. To address this, the aircraft was equipped with a sophisticated environmental control system designed to provide heat and protect the crew from the harsh conditions. The heating system was specifically focused on ensuring that the cockpit remained habitable for the crew, with heat distributed effectively throughout the area. Additionally, electrical heating circuits were incorporated to warm the crew's equipment, enhancing their comfort and safety during long flights in freezing conditions. Critical areas of the aircraft were insulated with specialized materials to prevent heat loss and safeguard both the crew and sensitive components. In the early stages of the Flying Fortress's operational history, crews relied on sheepskin clothing to protect themselves from the extreme cold. As the war progressed and technology improved, later variants of the B-17 introduced electrically heated flight suits, such as the Blue Bunny F-1 suits. These suits were designed with innovative features to ensure crew members could remain warm even in the most frigid conditions. However, despite their forward-thinking design, these suits faced reliability challenges, particularly with the internal wiring, which was prone to breaking during use, leading to intermittent performance issues. Despite these setbacks, the system represented a significant step forward in addressing the environmental hardships faced by the crew during long missions at high altitudes. The B-17's emergency systems were designed with a comprehensive focus on crew survival, ensuring that each crew member had access to the necessary equipment in the event of an emergency. Every position in the aircraft was equipped with specialized gear, particularly tailored to ensure the crew could safely bail out if required. A key component of the system was the provision of multiple types of emergency oxygen supplies, ensuring that each crew member could receive life-sustaining oxygen during critical situations. The primary emergency equipment included H1 bailout bottles, which were designed specifically for use during emergency parachute descents. These bottles provided a reliable source of oxygen for the crew members while they ejected from the aircraft, ensuring they could breathe during free fall. Additionally, portable 4 walk-around bottles were available, offering 12 minutes of oxygen for each crew member. These bottles were designed to be carried by the crew in emergencies, providing an essential backup of oxygen in case of sudden depressurization or the need to evacuate the aircraft. Each crew station also featured emergency oxygen hose connections, allowing for easy access to supplemental oxygen as needed. Engineers designed the oxygen system with 4 independent subsystems, ensuring that damage to one section wouldn't compromise the entire network. The G1 oxygen cylinders incorporated innovative leak-before burst design criteria, featuring external hoop and longitudinal tear straps that prevented catastrophic tank ruptures. The ball turret position presented unique engineering challenges, requiring specialized F1 oxygen cylinders mounted directly to the turret frame. These smaller tanks needed regular refilling, typically providing only 2 hours of oxygen supply. This limitation necessitated careful mission planning and coordination with other crew members. Intercom checks every 15 minutes, starting with the tail gunner and working forward, ensuring continuous monitoring of crew oxygen status. This systematic approach to crew safety represented a significant advancement in military aviation, establishing protocols that would influence future aircraft design. The engineering team integrated relief systems at each crew position, with the notable exception of the ball turret gunner's station, where space constraints required alternative solutions. This attention to basic human needs during long-duration missions demonstrated the comprehensive approach to crew support system design in the Flying Fortress. Testing and validation. Rigorous testing and validation formed the foundation of the B-17 Flying Fortress's development, with Boeing engineers conducting extensive evaluations at their Seattle facilities. The testing program established new standards for military aircraft validation, combining wind tunnel analysis, flight testing, and combat performance evaluation. Boeing's engineering team conducted crucial wind tunnel tests of the B-17 at Plant 2 in Seattle, where engineers Val Nelson and Bob Withington oversaw critical aerodynamic evaluations in March 1944. The original B-17 EF wind tunnel model, discovered years later in a Boeing warehouse, revealed the extensive testing conducted since November 1940. The wind tunnel testing program focused on several key areas, such as tail section aerodynamics for improved control, wing modifications for enhanced lift, defensive armament positioning, and high-altitude performance characteristics. Engineers utilized a sophisticated wooden and metal scale model that proved invaluable for testing modifications. This same model later contributed to improvements in the Model 307 Stratoliner's wing design, demonstrating the broader impact of the testing program. The flight testing phase validated the B-17's capabilities across multiple performance parameters. Testing priorities included high-altitude performance verification, combat maneuverability assessment, defensive system effectiveness, and structural load limitations. The aircraft underwent extensive modifications based on test results, particularly focusing on the B-17's distinctive tail design. This variant marked the first Boeing aircraft featuring an enlarged tail section for improved control and stability during high-altitude bombing missions. The B-17 was subject to rigorous testing to ensure it met the high standards required for its operational missions. One of the key parameters evaluated was the service ceiling, which determined the aircraft's maximum operational altitude. The B-17 demonstrated the capability to operate effectively at altitudes of up to 35,000 feet, ensuring it could carry out missions at high elevations, making it less vulnerable to enemy interceptors. Another critical parameter was payload capacity, which measured the bomber's ability to carry a substantial bomb load. The B-17 could carry a combat load between 4,000 and 5,000 pounds, providing it with the necessary payload to strike strategic targets with significant force during bombing runs. The effectiveness of the aircraft's defensive coverage was also a key consideration. The B-17 was equipped with multiple gun positions, offering full 360-degree protection for the crew, ensuring the bomber could defend itself against enemy aircraft attacking from any direction. This comprehensive defense system was vital for the aircraft's survivability in hostile airspace. Finally, the range of the B-17, or its combat radius, was another important performance measure. The aircraft could cover a combat radius between 1,000 and 2,000 miles, allowing it to conduct long-range bombing missions deep into enemy territory. This impressive range was essential for the bomber to reach distant targets while maintaining operational effectiveness during extended missions. Together, these parameters ensured that the B-17 was a formidable asset capable of carrying out strategic bombing operations under a variety of challenging conditions. The B-17's combat performance validation occurred through extensive operational testing. The aircraft demonstrated remarkable effectiveness, delivering over 640,000 tons, accounting for 42.6% of the total 1.5 million tons of bombs dropped on Nazi Germany and occupied territories. Through rigorous combat evaluation, several key performance characteristics were identified. The aircraft proved effective at operational altitudes up to 35,000 feet, thanks to its enhanced turbochargers, allowing it to reach and maintain high altitudes necessary for its missions. Additionally, its defensive capabilities were thoroughly tested, and the B-17 showed strong resilience against attacks from enemy fighters, which were a constant threat during bombing raids. The B-17's structural integrity was also assessed under the harsh conditions of combat, and the aircraft held up well even when subjected to damage from enemy fire. This durability made it a reliable choice for long and dangerous missions. Moreover, the B-17 demonstrated a high level of adaptability, proving its versatility in performing various roles, from strategic bombing to reconnaissance, further cementing its reputation as a dependable and highly effective aircraft during the war. The United States Army Air Forces utilized the B-17 across 32 overseas combat groups, with the total inventory reaching 4,574 aircraft by August 1944. Combat testing validated the aircraft's effectiveness in multiple roles beyond strategic bombing, including photographic reconnaissance, air-sea rescue operations, personnel transport, and long-range bombing missions. The testing program's success led to continuous improvements, culminating in the B-17G variant. This model incorporated all previous testing-derived modifications, including enhanced defensive armament and improved engine performance. The comprehensive validation process established the Flying Fortress as a cornerstone of Allied air power, with testing data directly influencing future aircraft development programs. The aircraft's performance in the Pacific theater provided additional validation data, with early B-17s conducting the first American bombing raids against Japanese shipping and airfields. This real-world combat testing demonstrated the aircraft's versatility across different operational environments and mission profiles. The B-17 Flying Fortress is a remarkable achievement in wartime engineering, combining innovative design with exceptional combat durability. Its advanced features, like the four-engine configuration, robust defensive systems, and structural integrity, made it one of the most prominent names in the military aviation industry. The aircraft's success was reflected in its ability to deliver over 640,000 tons of ordnance during World War II, and its legacy in shaping future aircraft designs. Boeing's engineering brilliance was evident in every aspect of the B-17, from its flight controls to its crew support systems, ensuring it could withstand intense combat damage while keeping crews safe. Its enduring influence on aviation design principles continues today. Let us know in the comments. If this video was helpful to you, please give us a like and subscribe to the channel. Thanks for watching.